Hello all, hope all's well. I'm going to finish up that 5.2 homework for you, the problems I couldn't get to in class. We'll start off with number 27 here. Number 27 asks us to do a right Riemann sum. We're given a right Riemann sum to estimate the height above the Earth's surface 62 seconds after liftoff. So we're going to stop here. We're not going to include this last data point there. We're not going to include that. We're only going to do the first, up until 62 seconds. And it asks us for a right Riemann sum. The first thing you'd want to notice if you're doing this problem is that our intervals are not of the same width. We have an interval of 10, an interval of 5, an interval of 5, an interval of 12, 27, and 3. And we're only going up through 62 seconds here. We're only interested in the distance that this thing traveled in the first 62 seconds. Notice you are actually estimating the area underneath a velocity versus time graph like I drew up here under the watchful eye of Bernhard Riemann. Don't worry, buddy, we'll make you proud. So for these first 62 seconds, we want to estimate this area underneath the curve. So what we are going to do is we are going to use the right endpoints. We are going to exclude the leftmost endpoint and only use the right endpoints to make our approximation. So for our notation here, we're going to be starting at I equals 1. We're going to be going to 6. And we are going to be multiplying the velocity at some time times the delta time, the change in time. And when we write this out, what you'll have is 185 is our first velocity, and we're going to multiply that times our first interval, which is 10. Then we're going to do our interval of 5 is going to be times the 319. We're going to do another interval of 5 times the 447. We're going to switch this up to 12 when we get to the next interval, so it's going to be 12 times the 742, and so on and so forth. And we're going to stop when we get to plus the 3 times the 1445. And this turns into, notice the feet per second is being multiplied times a seconds. This 10 of this first interval, that is a second right there. That is representing 10 seconds. And when I multiply those seconds times feet per second, think about what happens to those units. Seconds times feet per second. The seconds will cancel out and I'm left with feet. And that's the answer that you should give your, the units you should give your answer in. This is 54,694 feet. Okay, that's a right Riemann sum. There was a slight typo in your book, you may have noticed. It says use a right Riemann sum with 7 intervals. It's just indicating that we're using this data up here. But since it asks us to stop at 62 seconds, we're going to stop there. And we're only going to do those 6 multiplication problems to get there. Okay, I'm going to go ahead and skip 29 for now. And I'm going to go to 32 and 33. And 32 and 33 are kind of add-on questions. I will not ask you questions like this. I will not ask you questions like this on a quiz or a test that I write. This has never been tested on the AP exam. But let me just type something quickly for you. I'm going to stop the tape for just a second, stop the video for just a second, and I'll be right back. So 32 and 33 turn on this idea. If the graph is concave up, the trapezoidal approximation is an overestimate and the midpoint is an underestimate. So if a graph is concave up, that means it's shaped like this, okay? The trapezoidal approximation is going to be an overestimate. I'll be a little bit dramatic here with my trapezoid, but you can really see if I make a trapezoidal approximation, all of this is counting as an overestimate. And the midpoint is going to be an underestimate. Well, that might be a little bit unclear to you. Notice the graph is increasing. So there's going to be, if we think about the midpoint, there's going to be more area underneath on this side than there is on the left-hand side. So that makes our midpoint an underestimate. With a concave down graph, trapezoids will give an underestimate and the midpoint will give an overestimate. Again, this is not something that has ever been tested on the AP exam, but in theory, it's something I suppose they could test on something like this. So in this case, for number 32, here, I believe, let me just, so for number 32, the answer is C. In this case, we cannot rely on that being true. We don't know if the midpoint will indeed be less than L sub n plus R sub n all over 2. All of those other things, this in number 32, it tells us that the graph is concave up. And if it is concave up, trapezoid is an overestimate, midpoint is an underestimate. And you can think about if it, in this number 32, it also tells us the graph is increasing. So if it's increasing, think about what your LRAM is going to be. Your LRAM is going to be an underestimate as well. So it's going to be less of an underestimate, it's going to be more of an underestimate than the trapezoidal. It might be worth your time to kind of try to think that through. And I'm happy to talk with you about that in person. 33 is B. 33 is a difficult question to get, I think. It really just turns on this idea that if something is decreasing and concave down, then if the graph is concave down, the trapezoids are going to give an underestimate, the midpoint an overestimate. It turns on that idea. All right, let's move on to number 39. 39 is a question we are going to practice more in the next section. And this style of question, I think, is a really challenging style of question. And it is something that has been asked, I don't want to say frequently, but not infrequently on the AP exam. These are not considered easy questions. I want to make that clear. So we're giving this limit as n approaches infinity. And then we have I equals 1 to n. We have 3 plus 6 over ni squared plus 1. And then we have this 6 over n. Now, based on our class today, hopefully you can tell that this is actually equivalent to an integral. Okay, this is the equivalent to some integral f of x dx. And in this case, I think if you don't get this, then it would behoove you to try to figure this out. I think it should be clear to you that that 6 over n is representing the delta x. That's representing the delta x. And in this case, the delta x is formed, if we recall, it's formed by doing that b minus a all over n. So we know we have these endpoints a and b, and we know that they differ. In this case, they differ by 6. So that tells us that a to b is going to have a difference of 6. Now, what is the function that we're looking at? Well, if we're looking at this, what is this thing, this 3 plus 6 over ni? Well, that 6 over n, that's our delta x again. All right, then we have this variable I, and then we're doing something to this thing, and then we're adding 1 to it. These take some getting used to, and we will be getting better and better at these. But what are we saying we're doing here? I think it's easier, especially at the beginning with these problems, if you kind of think them through backwards, if you kind of think it through with the answer in hand, and think about how you might have got there. What this is actually saying is, think about the curve f of x equals x squared plus 1. If you think about what that curve would look like, it would be a parabola. And if we start at 3, notice, and I'm gonna give you some more guidance on this in class, but this number here, this is always going to be our a. That's going to be where we start. If we start this thing at 3 and we go until 9, what this is indicating is I'm plugging in some value. I've started at 3 and I've worked over delta x times I. That's my ith rectangle. Remember we talked about that idea today as we have some arbitrary rectangles over here. We have some arbitrary rectangles. And if I pick one of my arbitrary rectangles and I pick a point in here, how far over? I started here and I worked over 6 over n times I to get to this point. And if I think about what I would do to get the height of this thing, I would plug that value and I would plug in that x value, which would be 3 plus 6 over ni. I would square that and then add 1 to get the height. This whole thing represents my height. So this is the integral from 3 to 9 of x squared plus 1 dx. What this really is this is a midpoint Riemann sum of, this is representing this integral. the integral from 3 to 9 of x squared plus 1 dx. In other words, it's the area underneath the curve from 3 to 9 of x squared plus 1. Now this problem had even another twist to it because it actually asked you to do a midpoint approximation for this area, and it asks you to use 3 subintervals. So if I were to write that out, all right, my 3 subintervals would be, the endpoints of these would be 3 to 5, 5 to 7, and 7 to 9, and my midpoints would be 4, 6, and 8. So my approximation here, my midpoint approximation, would be my interval size, which in this case is 2, times f of 4, plus my interval size, which is 2, times f of 6, and my interval size, which is 2, times f of 8. And that would be actually your answer here. So the value of this thing actually comes out to 238 if you multiply all this out. That's an extremely challenging problem, but one I'd encourage you to spend some time with. This is not the kind of problem you're just going to get right away, but I would encourage you to spend a little bit of time and working backwards. If you think about working backwards and taking this integral and making it back into a limit problem, for a lot of you that might be the easiest way to approach this. Timmy is beckoning. What is it, Timmy? Oh, all right, buddy. Here. Let's try to look at number 40 as well before I have to let you go. I only get 15 minutes on this. So here's number 40. So number 40 gives us this Riemann sum. And this is based on a problem that was number 30 on the AP exam back in 2017. Now, number 30 is usually a pretty tricky question. You're talking about the end of the multiple choice section. And obviously they didn't give you the whole multiple choice problem in the Stewart book, but it's really based on that question really closely. So what is this? Well, this is 1 over n, and then it's 2 over n, and then it's 3 over n, and then it's n over n. So if we think this through, what is this estimating? So first of all, this 1 over n, all right, this is obviously going from an a to a b that differ by 1. Why is that the case? Because that 1 over n is my delta x. That's my b minus a over n. All right, that's where that 1 over n is coming from. So my a and my b have to differ by 1. And then I'm feeding things into a function, and it looks like the function that I'm feeding things into might just be the square root of x. Again, this is another problem where, for now, it might be easier for us to think this through kind of using kind of like a backwards approach and kind of thinking about what would lead to this result. In this case, what we're actually doing is we are doing a right Riemann sum here. This is the right endpoint approximation of f of x equals the square root of x from 0 to 1 using n rectangles. Again, if I think about this, like what would I be doing here? I'd be splitting this up into a bunch of little rectangles. So think about the square root of x. This is what this graph would look like, the square root of x. And if I go from 0 to 1, all right, and I kind of think like, okay, I'm going to work my way over. All right, let me get a different color here. I'm going to work my way over and I'm going to draw myself a little rectangle. And I'm going to work my way over and I'm going to draw myself a little rectangle. These things that I am, these points that I am putting into this are going to, each one of these is going, this is going to be 1 over n, this is going to be 2 over n, this is going to be 3 over n. If my interval is 1 over n, I'm working over by 1 over n. So these right endpoints are the heights of these right endpoints are just going to be the square root of 1 over n, the square root of 2 over n, and so on. And then my width for each one of these is just going to be 1 over n. So this is a right endpoint.